We are starting a unit called Forces at a Distance, which is where we look at forces that don't touch each other. We've already sort of looked at gravity, but not in depth. So we're going to be looking at different forces that can take place without touching things, without contact. So it's not like a normal force or a tension force or a pushing force or a friction force. So in order to understand one of them, we do have to understand a little bit about circular motion, and we've skipped that. So we are going to go backwards and look at circular motion. So imagine you're on a merry-go-round. So here's a little boy and his mom on a merry-go-round, and they're going in a circle. The question is, who is going faster? So if you can imagine this turntable, right? And we've got the boy is making a circle, the blue circle, and the mom is making the red circle, and they're both making maybe 1 revolution per minute, let's say, right? But you can see that the boy who's on the outside, right, the blue one, the one that's on the outside, he has to go a bigger distance in the same time. So it's kind of a trick question because they are rotating, revolving at the same speed, but if you look at their linear speed, if they were going in a straight line, the boy is definitely going faster because he's got a bigger radius, is going to equal a bigger speed. But this is if we're talking straight line motion. So when we look at circles, we're talking about something called periodic motion. It's motion that repeats, right? You go in a circle once, and then you go in a circle twice, and you go in a circle 3 times. So you're repeating it, repeating it, repeating it. So it's considered periodic motion. It's not the only type of periodic motion, but it's the only one we're going to look at. There's things like pendulums and springs and other things that do this, but we're just going to look at circles. So the period is the time for one cycle. So you want to add that to your units table. So you're going to add period and T and S to your units table because that is the time it takes to go around one time. Right? So it's one cycle. Frequency, on the other hand, frequency is an F, is measured in what's called hertz, which is really a 1 over seconds, right? This hertz, which is equal to 1 over seconds. It's also known as cycles per second. But we're going to use hertz when we look at it. And so the equation we want to add to our equation sheet is that F is equal to 1 over T. They're the same thing. But if I have a high frequency, I have a low period. So if you listen to a tapping pen, that has a low frequency and a lot of time between taps. And if I speed it up, you can hear the high frequency, but it's got a small time in between. So they are inverses of each other, but they're both a measurement of speed. It's just in different units and in different ways to think about it. So when we're dealing with circular motion, speed is still d over t, just like it's always been. We're not looking at velocity, we're looking at speed. Well, if I go around in a circle, we know that that is 2 pi r, right? Because the circumference of a circle is 2 pi r. So that is my distance. And we just said that the time to go around once is t, so that leads me to the equation v is equal to 2 pi r over t. V is directly proportional to R. So the bigger the radius, the bigger the speed for the same period, right? Because you have to get a bigger distance around. Now notice that this V is speed. It's what we know as linear, and sometimes you'll see it as tangential, which is a really big word. Don't get scared about it. It's just if I went off tangent at this speed, at this point, that's the speed that I would have. So linear speed, tangential speed is this V right here. It's not the circle speed. Frequency is kind of the circle speed. Now, for an object to move in a circle requires a change in direction, which means there's a change in velocity. So here's my satellite. It's going around this planet, and that means its velocity goes here and then here. So even if it's going at a constant speed, its direction is constantly changing. And we all know that to change velocity requires a force, right? According to Newton's laws, you need a force to change the direction. So you might see how circular motion is coming into play with forces at a distance. So that force is known as centripetal force. Please don't, I'm not even going to write it. The other word, I'm going to say it once and then we shall never mention again. Centrifugal. That is not a real force. Centrifugal is that outward feel that you have. If you're going in one of those amusement park rides, you feel like you're going out. If you're spinning, you feel like you're going out in your car. But that is due to inertia. The force that we deal with in physics is centripetal. So centripetal is center seeking. That's what it means. So centripetal acceleration and force are always inward. So I'm trying to go this way, centripetal force pulls me this way. I try to go this way, centripetal force pulls me this way. So no matter what I do, centripetal force keeps pulling me in. It's always inwards, even if it feels like it's outwards. The equations are very hard to derive, so you're just going to have to believe me. Fc is directly related to mass and velocity. So if I have more mass, more inertia, more speed as I'm going in my circle, right, that means I'm going to have more Fc. So notice it's on top of the fraction. And Fc is inversely related to r. So if I have a bigger r, it's going to be easier to make the turn than if I have to make a really tiny turn. And there's a little more to it than that, but for now, let's just look at that. And AC is v squared over r. And again, I can't derive it for you, but you can see that FC is equal to MAC. So if I just looked at my AC and I just stuck an M in front of it, you could see I'd end up with MV squared over R. So those are more equations to put on your equation sheet, and then we'll be doing some sample problems.